Okay, so today we are going to be looking at acids, bases, and pH in this video. So we're going to talk a little bit about pH, and we'll show you how you can go about starting in on some of these pH calculations. So to start with, we need to kind of talk a little bit about water, right? So we know that water is a molecular compound. We also know that water has a pH of 7, right? We always talk about water as being neutral. So what we don't really spend that much time talking about, though, is that water has the ability to self-ionize. So what that means is that one water molecule can react with another water molecule. Okay, this reaction isn't super favorable. And when I say it's not super favorable, that means it doesn't go to completion, right? Remember we talked about acids and bases as being strong or weak. We talked about that idea of how far to completion do they go, right? And we said that for things that didn't go very far, we were going to use those double-headed arrows. Okay, so this reaction only goes a little bit, but what happens is one of these waters gains a proton from the other one. So one loses and one gains. So one of our waters gains a proton to turn into H3O+, so it turns into hydronium. The other water lost that proton, and so it turns into hydroxide. Okay, so this is our water autoionization or self-ionization equation, where water reacts with water to produce that hydronium and that hydroxide. So what we find is that at 25 degrees, which in chemistry is generally what we consider room temperature, the concentration of the hydronium ion is 1.0 times 10 to the negative 7 moles per liter, which is quite a small concentration. Okay, we find that the concentration of the hydroxide ion is also the same. They are equal to each other, right? They're both equal to each other, and they're both equal to that 1.0 times 10 to the negative 7. And that's generally why water is considered neutral, because it has a balance between the hydronium and the hydroxide. When we consider acidic or basic solutions, we find that that balance starts to change. So in an acidic solution, if you think about that modified Arrhenius definition, we talked about acids having the ability to produce hydronium. So in an acidic solution, we find that there's significantly more hydronium ions than there are hydroxide. We find that in a base, it's the opposite. We have way more hydroxide than we do hydronium. So we wind up with this imbalance, which is why we find that we have different pH numbers between those acids and bases. So when we consider our pH scale, right, generally we talk about pH as being anywhere between 1 and 14, where we say that 7 is considered neutral, and then below 7 is an acid, and above 7 is going to be our base. Okay, you will find that although we use 1 and 14 as kind of the ends of this scale, they are not actually the ends. Okay, I can get pHs of like 15 and 16 if I have a really strong base at a high concentration, and I can get pHs down here below 1, where I could get a 0. I could even get a negative pH if I have a strong enough acid at a high enough concentration. Okay. So how are you going to calculate pH? We have an equation for this, and it's that pH is equal to negative log concentration of that hydronium ion, right? And so this is why in that last lesson, I was like, don't move to this one until you're able to calculate that hydronium ion concentration, because if you can't calculate hydronium, you're going to have a really hard time calculating pH because you won't actually know what that number is that goes into here, okay? Sometimes you'll see pH referred to as power of hydrogen. So basically it's giving us an indication of how much hydrogen ions or hydronium ions we have present in our solution, okay? So log, it's a button on your calculator. You will learn about logs when you take Math 30, for sure -1, I'm not sure about -2. But log right now is literally just a button on your calculator. So for those of you with a TI, if you find the number 7, which you all should be able to find pretty easily, you'll see that the button immediately to the left of that is a log. For those of you that have a Casio, as you know, I'm not really sure where it is on the Casio, probably somewhere in that vicinity, but it literally says log on the button, okay? So how you would type something like this in your calculator, you would use the negative button, not the minus button, the negative button. You would do negative log, and then you would enter whatever that concentration of the hydronium ion is. So if the question gives you the concentration of hydronium, like it says, oh, the concentration of this is 2.5 moles per liter, then you can go right ahead and you can just plug that right into this equation and get an answer. Some questions will do that. Most questions, though, are not going to do that. Instead, what they're going to do is they're going to give you the concentration of the acid. And so that means you have to do a little bit more work, because this equation isn't negative log concentration of acid, it's negative log hydronium. So I would actually have to go calculate my hydronium so that I could then plug it into the question itself, okay? And that is definitely far more common. Like I would say 99% of questions are going to require you to write an ionization equation and at minimum do a ratio before you plug into this equation. Very few will actually give you this value and have you plugging it right into it, okay? So we're going to start by just calculating what is the pH of water. You already know it's supposed to be neutral, but let's make sure that our equation actually gives us that, right? So on that first slide, when we looked at it, I told you that at 25 degrees, the concentration of hydronium is 1.0 times 10 to the negative 7. So givens-wise, the one thing that you have been given in this question is actually that concentration of hydronium. So this is one of those few questions that is actually giving you this. Most of the time, they do not, okay? And this is moles per liter. Oh, I need to do that. So because I already have the concentration of hydronium, I can go right into my pH is negative log, sorry, I missed the negative, concentration of that hydronium, right? When I look at that equation, I have all those pieces that I need to actually be able to plug into this. So we're just going to do equals negative log, and then we can put that concentration in. Okay, when we are calculating pH, pH does not have a unit. So this is one of the few times you'll notice that I didn't put that moles per liter in. That's because I don't need to put it in, okay? So we're going to do negative log of 1.0 times 10 to the negative 7. My calculator gives me just 7, okay? We have to take care of significant digits, so 0.00. Okay, and we have that because when we look up here at this number, we have 2 significant digits here, right? So some of you might be saying, whoa, hold up. This has 3 sig digs. There's a 7, a 0, and a 0. So what you actually find is pH has some weird sig dig rules, okay? So what you find is that in pH, the number before the decimal place doesn't count as a significant digit. Okay, the reason it doesn't count, and you'll figure this out when you learn about logs next year in math, is that number before the decimal being 7, it came from this, the exponent on my times 10 to the power up. You're always going to find that the number before the decimal is either going to be the same as that number or it'll be 1 off. So if this is a 7, either this is going to be a 6, a 7, or an 8, and that's just a reflection of this. So because when we identified our significant digits, we said only these 2 were significant, we've never identified this as significant, and that's because it's not. And that's why when we get into our pH numbers, this number here doesn't count as significant because it's coming from this exponent. These 2 numbers here are what count as significant because they're reflecting this, okay? So weird rule, but it's important in Chem 20 and in Chem 30 to know that when it comes to pH, and the same is going to hold true for pOH, it is only the numbers after the decimal that count. Okay, not true for concentration. Concentration is a normal number. This has 2 sig digs. But this pH over here, I'm only carrying about 2 numbers after the decimal place. So anytime you are calculating a pH, go up to your question, figure out significant digits, whatever it is, that's how many decimal places you can have. Okay, not how many total sig digs, which is our normal sig dig rule. It's going to be how many decimal places we have. Okay, sorry, I'm getting a reminder that I have a meeting in 15 minutes. Okay, so let's look at this one. So a little bit different. So calculate the pH of a solution with an HCl concentration of 3.8 times 10 to the negative 3 moles per liter. So this is different than the last example. And the reason it's different is I was given the concentration of HCl. You think about the equation that we have. Okay, our equation is negative log of hydronium. I don't have hydronium, I have HCl. So we can fix that though, right? Because we know how to convert concentrations. We know that we can write an ionization equation, right, where we react this with water to give us that hydronium. Wrong buttons, too many buttons. Plus that Cl minus. Okay, so from here, we can calculate what this is, right? And we need to calculate this so that we can figure out the pH. Right now, what I know is the concentration of HCl as 3.8 times 10 to the negative 3 moles per liter. Okay, so we have to calculate our hydronium ion concentration. We are going to calculate that, didn't hit the right buttons, by doing our unit analysis, just like we always do, right? So remember in our last video lesson, we looked at how we could convert, didn't mean to do that, between the HCl concentration and the hydronium ion concentration. We said we could simply use a ratio to do that. So we're going to do 1 mole of our H3O plus. That's going to be over that part, 1 mole of HCl. Okay, we need to get rid of moles of HCl, so we are going to times by 3.8 times 10 to the negative 3 moles of HCl per liter. Right now, when we look at this, moles of HCl cancels out. We are left with moles of hydronium per liter. Okay, so when we do this on our calculator, because it's a 1-to-1 ratio, we get the same answer that we started with. Okay, there's usually somebody's like, well, Ms. Chip, if it's the same answer, why did I have to do all of that? And the reason you have to do all of it, well, there's 2 reasons. One, there's marks for it. You want to make sure you get full marks, that you don't lose marks for something. The other thing is, it's not always a 1-to-1 ratio every single calculation that we do, right? And if we just start always assuming that it is and that I can just use this number and plug it right in, I might be right sometimes, but I might not always be right, and I may wind up getting the wrong answer. Okay, so now that I've actually calculated the concentration of hydronium, then I can go about calculating that pH, because we know that it's equal to negative log concentration of hydronium, which we have now just calculated. So we can say that it is equal to negative log of that 3.8 times 10 to the negative 3. So one thing to point out, we're using the answer from this to do this. In this case, I have a nice whole, well, not whole number, but I only have 2 digits to it. But if I had like a weird number, please make sure you use the answer button by the time you get down here. Sometimes you guys round this number, and if you round this number and then use the rounded number in this calculation, it winds up giving you the wrong final answer, okay? So let's actually calculate what this is. We're going to do negative log. Oh, I'm in some weird setting on my calculator. Okay, so we do our negative log of 3.8 times 10 to the negative 3, and we get 2 point, and remember, this had 2 significant digits, so that's going to mean 2 numbers after the decimal place, 4.2, okay? So a question like this, for the most part, is going to be worth 3 marks, okay? Where those marks are coming from. One is coming from this, my ionization equation. One is coming from this, my unit analysis with my ratio, showing that I recognized I needed to convert HCl over to H3O plus. And the third mark is going to come from this pH calculation, right? So looking at how many marks a question is worth is really helpful for deciding how much work you need to do, right? If it's a 3-mark question and this was all I did, I should be questioning, did I actually just do 3 marks worth of work? And if I feel I did, then okay. But personally, if I only did this and a question was worth 3, I'd be questioning, what did I miss? Because there's no way that this just little calculation is actually worth 3 marks. Okay, so let's look at one that's a little bit more complicated. So now you're being asked to determine the pH of a solution made by dissolving 3.75 grams of HNO3 in enough water to make a 250 ml solution. So we've been given information for nitric acid. To calculate pH, we need to get hydronium. So again, we're going to have to write that ionization equation to start off. So we're going to do the nitric acid plus the water. Okay, that's going to give us our hydronium plus our nitrate. Okay, so to be able to get pH, we need to figure this out, right? Right now, we don't know what this is, so we need to, figure what that is. Once we figure that out, then we can figure out what our pH is. So when we look at the givens we have, everything we've been given is for the nitric acid, right? We were told 3.75 grams in a 250 ml solution, so 0.250 liters. Okay, because we have a mass, we're going to have to go get a molar mass. So hydrogen, nitrogen, I'm not entering the right things, 13.01, and then 3 of those oxygens. We should be getting 63.02 grams per mole. Okay, so to get the concentration of hydronium, this looks exactly like the questions you did in the last lesson, right? We had to use our ratio and do our unit analysis to be able to get that. So we're going to start by calculating the concentration of that hydronium ion. So unit-wise, we're looking to get moles of H3O plus per liter. We'll start with our ratio. So 1 mole of H3O plus, because that's what we're looking for, right? That unit needs to be on top, over 1 mole of HNO3, because that's what we've been given information for and what I can eventually cancel out. So I need to get rid of moles of HNO3. I look at HNO3, it's over here. Here's something with moles. To be able to cancel it, it has to go in the opposite spots. We're going to do times moles, HNO3, right? We're going to flip that over 63.02 grams. Okay, looking at our units, we now can get rid of moles of HNO3. Next thing we need to do is get rid of grams. Well, we can use that 3.75 grams that we had. So times 3.75 grams, throw that over 1. Okay, now we can get rid of our grams. Last thing we need to do is place the liters, right? We look at all our units, everything is gone. All we have is moles of H3O plus. So to place those liters, we're going to do times 1 over that 0.250 liters, right? And that places those liters where I need them to go. So in our calculator, we're going to type all that in. So we're going to do the 1 divided by 63.02, then times 3.75, and then divide by 0.25. Okay, and we get 0.238, and it keeps going. So I'm just going to put dot, dot, dot. Okay, I'm going to put dot, 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 because I want to make sure that I know that there's more to the number, even though I'm not necessarily writing it all down, right? If you look at your calculator, there's a whole bunch of other numbers. But that's okay, because we can use that answer button that we talked about before. So now that I have the hydronium, I can calculate the pH, because it's negative log concentration of that hydronium. Okay, so this is where what you're going to do, oh wait, I forgot negative. So we're going to do negative log of that whole number. Okay, so when you type this in your calculator, I would suggest literally just doing the negative log and then using your answer button, right? So for those of you with the Casio, the answer is the second function of the negative. I think if you have a Casio, the answer button is its own thing, but definitely you should be able to find your answer button on there and just do negative log of that answer so that we're using the whole number. If you don't, you're generally going to find that your pH is going to be ever so slightly off. Usually that last digit that you write is going to be off by 1. And then if it's like a numeric response or something, you wouldn't get the marks for it because it wouldn't be the same number. Okay. So when I do this, I'm getting 0.62, and how many sig digs can we have? That had 3, so I get 3 numbers after the decimal, so 623. Okay. This is quite a small pH, but if we think about it, nitric acid is one of our 6 strong acids, and this is considerably, I don't want to say considerably high concentration, but it's a high enough concentration that this pH is not unrealistic for this type of solution. Okay. So when it comes to measuring pH, we kind of have 3 different ways of going about doing that. There's pH meter, which if we were actually at school, we'd be using when we did some of these labs. It's basically like a long stick with a little glass ball at the end. You stick it into your solution, you kind of swirl it around, and then there's a little readout on the meter that's going to tell you like the pH of the solution is 2.50, and then you can rinse it off, put it in another solution, be like, this one is 8.25 kind of thing. We have pH paper, which are those little strips that you dip in, they come out, they're different colors. We can figure out what pH number we have off of that. And then there are indicators. Okay, we have a lesson a little bit later on in this unit where we're really going to talk about indicators and the different ways that you can use them to determine what some approximate pHs are going to be. So diluting acids and bases, right? We talked about diluting regular solutions. We talked a little bit about diluting things when we talked about acid and base spills and what our options were. So one of the tricky things when it comes to pH and how it's going to change is as we dilute either an acid or a base, it's going to become more neutral, which means it's going to get closer to 7. So if we go all the way back to this slide here where we drew this little scale, right? If I have an acid, let's say, which has a pH of 1, and I dilute it, it's going to move closer and closer to 7 till eventually it hits 7. So in diluted in acid, its pH is going to rise, okay? And it's going to rise because as we dilute it, the concentration of the hydronium is going to become less and less. If you think of a base, it's kind of doing the opposite, right? If I start with a base, let's say it has a pH of 14, and I add water, I'm going to start to move it closer to 7. And so I'm actually going to see that its pH is going to become less. So the pH number of acids and bases do different things when we dilute them. What's the same? They're both approaching 7 or potentially getting to 7. But the change to the number is different, where acids are going to increase in number and bases are going to decrease in number. Okay, so make sure when you get questions about how's the pH going to change, you kind of stop and actually think about it. Sometimes you guys are just like, oh, well, I diluted it, it should become less, right? Like it's kind of just your general thing. I know dilution means I have more water, I have less solute. But really it's going to depend on whether I have an acid or a base. Okay, so those are some things to think about when you are diluting acids and bases and how that pH is actually going to change. Okay.